Hey guys, welcome to the third lesson on data structures using C++. Today we're going to be talking about linked lists. We're going to talk about what a linked list is. We're going to talk about how we can use it, what are some benefits of using it, and things like that. So a couple things before we start. The first thing is that we're going to essentially take everything we took from the last lesson, which was on array-based lists, and we're going to take the header file from that and all that, and we're going to convert it into a linked list implementation. So all the public functions and members are going to be the same depending on how we implement it behind the scenes. That's the whole point of this abstract data type that I was talking about that we are creating. The public interface will remain the same to the actual users, but how it's implemented behind the scenes will change. And we're going to be implementing this version of it using a linked list. Now, last time we used an array, like I said, an array is a basic data structure, that we're all used to, that stores items based off of indexes in memory locations, which is a good basic data structure. But sometimes you want other things. Sometimes you want to use other things, and learning things like linked lists, and we'll get some more down the road, allows you to add more tools to your toolbox. So when you sit down and you have a program to write, you can say, okay, what tools do I have? What are the benefits of using a linked list implementation rather than an array-based implementation? What are the pros and cons of each? And depending on what I'm going to be doing, which one should I choose? And that's where that's my job here. I want to help you guys to determine when you should use each implementation, when you should use certain things in certain types of scenarios. So the first thing we need to do the first thing we need to know and understand about linked list is, well, what the heck is a linked list? And if you understand pointers, you'll understand linked lists pretty quickly. A linked list is simply a way that we can store data, like an array. An array can store data, but it uses indexes and stores it in memory locations and uses indexes to access those locations. A linked list is another way that we can hold a bunch of data, right? We can hold a bunch of data, but in a different way. It's not actually going to be in an array. We don't actually need an array, and this could be shocking for people. If you are a basic programmer or a beginner programmer, and you probably thought the only ways to really store data are arrays, really. But there are other ways, and we'll get to even more ways, even past linked lists. There's tons of ways to do stuff. So yeah, a linked list is a way that we can represent and hold a lot of data similarly to an array. But what our job is to use a linked list as the code behind, or the framework, and we're going to make a container, and our container is going to be how the users add items and delete items and store items. Like, we're going to make it our container. Like, C++ has some containers in the standard template library, like a vector. If any of you know what vectors are, it's like a standard list. I don't know how it's implemented. It doesn't really matter. But so we're going to be doing a linked list implementation. This linked list implementation, like I said, is going to have the same exact public interface from the last lesson. So I'm just going to take that and copy it. So the header file is like this so far. So from the other one, I took most things. These are all from the last lesson. I added a destructor because we're going to need it. I also deleted the array in the private data because, like I said, we're doing a linked list, so we're not going to be using an array to hold data anymore. So let me go ahead and draw and illustrate what a linked list is, because I haven't even explained that yet. And hopefully once you understand what a linked list is, then you'll understand how to implement it. Okay, so essentially, to start off, a linked list, there's some terminology with a linked list. In a linked list, we create these things, and they're called nodes. And a node essentially holds our data of our item, of whatever it is. So if we're doing integers, our node will hold our integer value. But Also, besides just holding the actual value of it, nodes also hold a pointer to its next node. And this is for a single linked list. We're not going to get into double linked lists in this video at least. But yeah, for a single linked list, the node holds the data of the item. So if it's an integer, it could hold like the value 100. And then it holds a pointer to its next one. So how a linked list works is we have a pointer, and let's say we call it start. So we have a pointer called start, and this points to our first node. Let's say we had like 3 items. So in this first node, we got like the value 10 for the data portion, and then it also points to its next node in the list. So we get a picture that looks like this, where the nodes keep on pointing to the next node. So a couple things to note right off the bat if you're looking at this. You'll realize that the only way to get inside of this list is to access it through the start pointer. We don't have random access just to access it anywhere we want like we do with arrays. Arrays we can access anywhere we want with this index. We can't do that with a linked list. A linked list can only be accessed from the start pointer, and then each node knows where its next node is, and that's what actually creates the list. As you can see, it kind of looks like a list. This is what the list looks like. Now, there are benefits and downfalls to this, and I'll get into this more, but like off the top of my head, one big benefit of using a linked list over an array is if you know you're going to be adding lots of items into a collection, like items all the time, you might not want to use an array because arrays have set sizes, so that if you use an array and it gets past the size that you put in, you'll have to make it either grow or do something else to actually make it be able to fit more. So arrays have preset sizes which aren't the greatest for adding lots of items. So linked list, on the other hand, linked list can add an infinite amount of items until literally we run out of memory. And you don't have to worry about resizing or anything, because if you think about it, there's no structure that's around this, right? You could add more items by just creating another node, right, anywhere in memory, and just make the previous one point to that, and then now that's inside the list. So linked lists are really good with adding a lot of items into it. Now there's also problems, which we'll get to when we start actually implementing it. But yeah, this is the basic idea of what a linked list is. It's a node. Each square is a node, and the node has a data, and it points to its next node. And they keep on pointing, creating the list. And this is how we can store data in memory. So now that we did this, let's go ahead and create a node. So we need our first node so we can see how it works. So to create a node, I'm just going to make the node a structure. So let's go ahead and create our node type. So let's go add new item, header file. I'll just call it node type. Struct node type. So our node type is going to have our data portion, which is going to be an integer. We're only making a list that will hold integers, like our last example with the array based, and then it holds a pointer to the next node, like that. All right. So now that we have our data portion, and we have the pointer that points to our next node, now we can start hooking it up with our actual collection type that we're creating. So in our private data, like I said before, I took away that array that we used the last example, but the public members are the same. This time I'm not using an array. Like I said, I want to be using a linked list. So we have to use nodes, or the nodes that we created, because a linked list is the nodes connected to each other with the links. So I'll go ahead and include that, and then I'll say node type star for our pointer, and then I'll call it start. So the start pointer in this class is going to be the start of this linked list, or the start of our data. So now that we have that, now we can go ahead and start making the actual, or implementing the actual code. So let's go ahead and go to our CPP file for our unsorted type, and we're going to start implementing everything. The first thing we're going to implement first is our unsorted constructor. so the constructor has no parameters. And all we're going to do in the constructor is set the length equal to 0, like with the array, because I didn't explain this. The reason why we want to still keep the length property is because we want to make sure that we can keep that big O runtime of 1 when we're doing the getLength function call. If we keep track of the length by when we insert something, we make it go up, and when we delete something, we make it go down. If we do that, when we call getLength, we can just return the length field. If we didn't do that, we would have to go through the entire linked list and count them all every single time that someone did getLength, which would be a big O of n runtime. So we want to keep that big O of 1 runtime, so I'm going to keep track of the length using this field. So I'll set that equal to 0 in the constructor, and I'll also set start equal to null. By saying start equal to null, this is, well, I'm just saying start equal to null. We're going to be using this. This is important because we're going to be checking for things equal to null, and I'll show you what I mean by that. If I go back to my picture real fast, when you have a linked list like this, the last node in the list is going to be pointing to something. So like, let's say this had the value 10 in it also. The last, like, you may be thinking, where does this point to? Because each node points to its next node. Well, if there's nothing inside, if there's no other node after this, it does point to something. It just points to this thing called ground. It points to the ground, or aka null. So by setting the start pointer equal to null, that means there's nothing in the list. That means the list is essentially empty. So that's why we did that. Okay, so that is the constructor. The next, let's do the insert item. Now, remember what I said about the insert item? I said a few things. I said that the insert item has some benefits because the insert, I can't type and talk. Unsorted type, insert item, int item. The insert on a linked list has benefits because we don't have to always stay in the bounds of the array, right? If we want to grow, we always can grow. We never have to actually resize it like an array does if we run out of area. So that's a benefit of linked list. So the linked list, we want a big O. Let me put actually the runtimes here. Big O runtime of this is 1. This is also, I want to maintain a big O runtime of 1 for my insert also. So for this is gonna get this isn't too bad. So remember the steps of creating adding an element to a linked list. First is you have to create a new node because these are all nodes. So we have to create a new one and then add it onto our list. So the code is we first have to create a new node. So I'm going to say node type. I'll call it temp equals new node type. So there's our new node. We need to set the actual data for our node. That's going to be equal to item because that's what we're adding in. And then we also have to say temp.next. This is where this node points to. Where does this point to? This is a little tricky. And I'm going to type the code out and then I'll explain what's happening. So it's going to be temp.next equals the start. And then start equals the temp. Now, I'll explain what is going on here. And then the last thing is going to be length plus plus. So there's a few things to note. The first thing to note is because this is an unsorted list, we're doing an unsorted list, we need to add the node in the most efficient spot. If I didn't add it in, if I wanted to add the node into the end of the list, like if I added it in like this, how this picture is, if I added it to the end of the list every single time, we would have a big O of n runtime because we have to travel down the linked list to get to the end to add it in. Instead, it's more efficient because it's unsorted, we can do this. If we create, let's say we're creating a new node, like right here, it's more efficient if we create this new node and then we hook it up to the front. So what we could do is we could say that this node is going to be pointing to this one, and this start, instead of being pointed to that, the start will then point to the new one. That's what we're doing in our code. So instead of adding new nodes to the end of the list, we're adding it to the front of the list because that's more efficient. So that's simply all the code is saying. Now I'm going to take the code, I'm going to make a new picture, and I'm going to do line by line what the code's saying so you can see what's happening. So let's go ahead and create my start pointer first. Let me type this so it's not ugly. So start, this is my start pointer. So at first, start equals null. That's what the constructor says. So it's going to look like this. We have start, and it points to the ground, we can say. So start points to null. This is how it starts off. Let's say we insert 5. So we're inserting the item 5. What does the code say? The first line of code says create a new node. So let's create a new node down here. This is our first node. It then says set the data portion to the item that's being passed in. So I'm passing in the value 5, I'm inserting that. So now the data portion of my node will hold a 5. Oops, that's really ugly. Let's go ahead and do like this. So the data portion is holding a 5. And then the next portion, or the pointer portion, it says point to start. So this is interesting. So the line, it says temp.next point to start. So that means go like this, and the arrow is pointing to start, or essentially null. So that's what the picture looks like right now. So that's the first 3 lines. The fourth line says start equals temp. So that says, so temp is our new node. So this is our temp right here, and it says start equals temp. So to do that, that means that we say start, which is essentially null, is now going to be pointing to the start of the linked list. And this arrow is essentially pointing to null. So this is what the picture looks like now. So now we have a start pointer that's pointing to our first node, and then that node's pointing to null. That's what we told it. That those lines said this. Now let's add another item. Let's say we're going to add the number 10. So the first step is to create a new node. I'm reading this line by line. Put 10 into the node. That's the value we're inserting. Temp.next equals start. Temp.next equals start. So what is temp.next, or what is start? Start is pointing to this node right here, or this 5. So that means this node points here now. Now, hold on. This is getting a little bit confusing, but I'll explain. So that's that line. And then it says start equals temp. So then that means that we go ahead and now start, instead of pointing to that one, is pointing to this. So this is the picture we get. But look what happened. Start is the beginning of our list. So the first item is 10, because remember I said we add to the front. Then 10 points to 5, and then 5 points to null. It makes sense. It all makes sense. Now, you can logically, I can rewrite this and make it cleaner. Like, this is what it kind of looks like, but logically, I can clean it up. So essentially, it looks like this. We have the start pointer. Actually, we have the start pointer. Start points to, let's go ahead. So we have this. We have 10. Start points to 10. 10 points to 5. And 5 points to null. So 1 and 2 are both equivalent. You can think of it looking like this, but I mean in reality it doesn't look like this, because the pointers are really memory addresses and everything. But when we just insert items and you add it onto your picture, it looks like 1. But 1 is exactly the same as 2, just cleaned up a little bit. So when we add items, this may be confusing, but this is what happens. So like I said, one more time, we create a new node. We set the data of the node. We said that this node equals, the next is the start, and then the start is the temp, which is this one, and then length plus plus. So this is an insert statement. Okay. Next, let's go ahead and do the isFull function, because this is a pretty interesting function. So first, let's go ahead and set it up. Bool unsorted type is full. It's const. So the is full function simply returns true if it's full and returns false if it's not. We want to maintain the big O runtime of 1 for this function. So we need to think about this for a second, because I told you guys that essentially the only time a linked list could be full is if we are out of memory, because we don't actually we don't have the bounds of an array to stop us. So we're never full unless we're out of memory. So for this to happen, we have to set up a check to see if we're out of memory. And the way we do this is we actually try to allocate a new node, and if it throws a bad allocation exception, that means we're out of memory, and that's what we do. So it's pretty simple, but you may not have thought of this is how it's done, but really, yeah, this is how it's done. So let's go ahead and create a node called location, and we're gonna set up a try and catch little exception handling right here, and we're gonna say try to create a new node. So location equals new node type. So if this is successful, it will go to the next line of code. And if it does, we're just going to delete the location, because that's all we wanted to see. We wanted to just see if we had room to create this new node. In this case, then we'll return false because we have room. We're returning true if it's full. If it is full, when we try to do this allocation right here, we would get that exception being thrown. So we would do catch bad allocation exception. That's just the name of it. Doesn't really matter. And if that happens, we'll return true, saying we're full. So if we were full and out of memory, the exception would be thrown right here, and it would never execute delete and return false. It would jump right to here and hit return true if we're out of memory. So it never even allocated that memory. So this is our is full function. It's unique, but yeah, this is how it's really done. So this checks if we can, or if our linked list is full. Okay, next up, let's go ahead and make our make empty function. So let's go ahead and set this up. Unsorted type, make empty, and the make empty function is going to be a big O runtime of n in this case, because this is C++. We have to go through it all and release the memory. So if you're thinking, okay, we have to iterate through this, or we have to travel or transverse down this linked list, that means our big O runtime is going to be n, because we're gonna have to access every item in this linked list. So we're gonna have a big O runtime of n in this case. But the way we do this is kind of interesting. So the first thing we do is we have to create a temp pointer. And the reason why we have to create, I don't know, let's call it temp. The reason why we have to create a temp pointer is because if we're trying to transverse or travel down this linked list, if I use my start pointer and use that to transverse or transit down this linked list, I'll lose access to the previous things. So if I say start, go to the next one, so I can delete the other one, I'll lose access to it, and it gets really ugly. So I need this temp pointer so that this can travel, I can set this temp pointer to the previous one, so I can make the deletion while the start pointer goes to the next one, if that makes any sense. When we do the show function is going to have something similar like this, because the show has to transverse or travel down the entire linked list also, but that will be a little bit different. So we create the temp pointer, and we say while, this would be different, we're going to say while the start is not equal to null, because the start is going to be traveling down the actual linked list. The temp pointer is going to be the one we're going to delete. So we're going to say while start is not equal to null, temp equals start. So we're saying temp equals the first one. Then we're going to say, okay, now that temp is equal to the first one, start can travel to the next one. So I'll say start equals start.next. So now start moved to its next node. And now that start is gone, we can say delete temp safely. And we can delete temp, which is pointing to the first one. And then once we delete that, that's it. This will go through the entire thing, deleting each node. And I'll show you what I mean by this. I also have to set length equal to 0. So I'm going to illustrate this with drawing it again so you can see what it's happening. I'll go line by line and do what it's doing here. Okay, so let's say hypothetically when we get started, I'm going to say we have 3 items in our linked list just to start off with. So this points to that. This points to that. So we have 3 of them. And this obviously points to null. So we have the values 5, 6, and 7 in our linked list, and start is pointing to the start. So this is the picture we have, and we want to call make empty and delete everything. So the first line says allocate or create a variable called temp, which is a temp pointer. So we did that. It's over here. Then we enter the loop while start is not equal to null. Okay. We come in. The first line, temp equals start. So essentially, temp is now pointing to the start, which is the first node. That's the first line. Then it says start equals starts.next. Okay, that line makes start point to its next node. So that line makes this happen. Start equals starts.next. So now start's pointing to the next node. And now that we did that, now we can safely delete temp because start is not in there. If we didn't use the temp variable and we did delete start, then 6 and 7 will be memory leaks because we have no access to delete them. So we have to make sure that we don't get a memory leak and start goes to its next element. Now we can call delete temp, which will delete this. Okay, so now we have that picture. So now we're in the while loop. While start is not equal to null. Is start null? No, it's not. So temp equals start. So what happens is temp now points to this node. Start equals starts.next. So when that happens, we go ahead and make start now points to its next node, which is 7. Now delete temp. That gets deleted. Is start null? No, so we execute again. We come into the loop. Temp equals start. So temp equals start makes that point to starts, which is right there. Start equals starts.next. So that line of code makes starts points to 7's next. 7's null though. So what happens is start now comes around and points to this null value. So now starts pointing to null. This is null. So if people didn't know, that's null. So and then delete temp. So now we delete this safely. The loop ends. We come back while start is not equal to null. Is start null? Yes, it is. So we break out of the loop and then we set length equals 0, and that's it. That's the end of the make empty. So as you can see, this is what's happening to clean up our linked list. So that's the make empty function. While we're at it, let's go ahead and just set up our destructor, because our destructor is essentially just going to call make empty, because make empty is cleaning it up for us. So that's all our destructor really has to do. So this makes our destructor also big O of n in this case. Okay, so we did destructor make empty is full insert item. Let's do get length, which is very simple because we're keeping track of it. So it's a big O runtime of 1. So we're maintaining that big O runtime of 1. Int unsorted type. Actually, it's get length const. And all we're gonna do is type in return length. That's it. So we did make empty. We did is full. We did get length. We did insert item. We did show. Oh no, we didn't do show. Let's do show really quickly. So show just gonna show all the elements in the linked list. So void unsorted type show. Now, show is going to also be big O runtime of n because it has to go through the entire linked list. This is going to be very similar to the actual make empty function. We need that temp pointer because we need to, we need a temp pointer, but our temp pointer in this case, before we get into the loop, we can say temp pointer equals start here. And I'll explain this all after, like I always do. Then we'll say while temp is not equal to null. So this is showing you that the temp is actually going to be traveling it this time. Cout temp data and L, and then temp equals temps next. So in this case, we're saying temp because we don't want to lose access to the entire linked list. So we're not going to use the start to go over it. We're going to make it a temp. And the temp pointer is it's going to be what travels over the linked list. So we say temp equals start while temp is not equal to null, display the actual data, and then temp can go to its next one. And this is the same thing. It's going to keep on going to its next one, displaying. And then once temp is null, when it reaches the ground of someone's next, then it will stop displaying, and that's all you need. So that's the show function, very basic. So this is showing a linked list. So we did every single function here besides the hardest one, DeleteItem. So DeleteItem is hard, especially for beginner programmers. I'm sure some of you guys are going to have a lot of problems with this, but I want you guys, if you don't understand it, ask questions in the comments. Ask me for help because this can be tricky. And you're not gonna, even if you try to Google a solution for this, there's so many different variants and so many different circumstances and stuff like that it's hard to even find answers for how to do this. So if you don't understand, ask me and I will help you because depending if you're doing a sorted one, an unsorted, it can always change. So DeleteItem is hard. And well, let's first set up the actual body. So let's go void, or header, I mean. DeleteItem, it's item. The reason why DeleteItem is hard is because if we look at this picture, let's go ahead and make a new one. When we have these linked lists like this, or these nodes, I mean, sorry. When we have this, and let's say I wanted to delete this middle one right here. I want to delete this one. The problem with this is, once I delete this, I can't just delete it or be done with it because then the linked list would be broken. So I have to, after I delete this, I have to repair the links and make this one point to this then. And go around that essentially to make sure that the linked list is still intact. So that's the hard thing. And the reason why it's hard is because if I have a temp pointer that's traveling over this and to find the target to delete, if I land on the target and say, okay, this is the one I want to delete, I'm screwed because that's too late. If I'm on the target with my temp pointer and find it, how do I have access to the one before it? I don't. So then by doing it that way, if I find the item to delete while I'm on the item, how am I going to get the item before it's a link to the next one? I can't. So what I need to do is I need to always check from one behind and check the next node to see if that's the target and do it like that. So I'm going to go ahead and write the code and try to explain it the best I can, but if you don't understand, I want you to write comments and ask me questions. And I just want to point out, in the array, the unsorted, the array-based implementation, the delete was so simple. All we had to do was take the last item and swap it in for the whatever item we wanted to delete. It was very simple, but like I said, linked list is harder to do. Also, this is going to be a big O runtime of n because we have to obviously find the target. So the first thing we're going to do is we're going to make sure that there is even any items. So we're going to make sure if start is not equal to null. So if it's not null, then we'll go ahead and enter this. That's the first step. The second step is I'm going to make a first temp pointer that will go over the actual linked list. So node type temp equals start. So the first thing I want to do is, what if the item that we want to delete is the first? What if the item we want to delete is the first node? if it's the first node, we're going to do a check for that. So we're going to say if item, which is the thing we want to delete, equals starts.data or temps.data, doesn't matter. So that means that the item we want to delete is in the first node. We'll just say start equals start.next. So the start pointer goes to the next one, and then we'll just call delete on temp and length minus minus. So this is if the node that we want to delete is the first node. So we did it. We deleted the first one, but it gets harder. So let's say else. So if it's not the first node, then what are we going to do? So the first thing we need to do is we need to set up a loop because we have to go through each one, check and define the target. So we'll say while temp.next is not equal to null, meaning that the next one is not null, so we can check it, and item equals this is gonna be, hold on, let me type this out first and then I'll explain it. I'm pretty sure I can actually remove some of these parentheses. Yeah, I don't need that. No. Okay, so what this is essentially saying, actually I don't even need, why did I type all these parentheses? Okay, that's fine. So what this is saying right now, why is this there? Wait. That one. Oh yeah, I need another one, okay. So what this is saying is, first, while temp.next is not equal to null. Okay, good. And while the item that we're trying to find is not equal, because of this right here, so I'm saying, I could say not equal, or I'm saying while the item equals temps.next.data not. So while I'm saying, and the next item is not the target. That's what I'm saying. So while the next item is not the target, if it's not the target, we're going to go temp equals temp dot next. So if the next thing is not my target, then I'm going to go to the next one. Once my next one is my target, I'm going to break out of the loop. So once I'm broken out of the loop, then I know I either the item is not in the list at all, or B, I found my target. So what I'm going to do is I'm going to make another temp pointer, node type. I'm going to call this target equals temp.next, right? Because if we broke out of this, that means the next item is my target. It's the item that I want to delete, because the while loop checks the next item's data. So if the next item's data is not equal to my, or if it broke out, that means that the next item data is equal to my item. So that means that once I get out of the loop, the target is the next item. That's what I want to delete. Then I'm going to say if target is not equal to null. This check is because if it is equal to null, that means that the actual item didn't even exist in the list, because of this right here. While temp.next is not equal to null. So if it is null, that means the item was not in the list. So if it's not, that means it is in the list and we need to delete it. So we'll say, okay, so if the target is not equal to null, like I said, meaning that we found the target, I want to say temp.next equals targets.next. Now I'll explain this all again. Then I'll delete target and length minus minus. So this is the entire delete function. So what I'm going to do is I'm going to go through the entire thing explaining it, and then I'm going to go through the entire thing drawing it out so that we can understand it. Okay. So first, I think we can all understand this top part. I'm saying I'm creating a temp equals start, and if it's the first one, we make the start go to the next pointer and we delete the temp. That's basic. Else, that means the item is somewhere else in the list. So the while loop says while target.next is not equal to null. So while the next target is not null, That means we're good to go. And while the item while the item is not equal to the temp.next.data. So that means that the temp pointer, the next one that we're going to check, before we even navigate to that one, we're checking it beforehand. So the next one, if that data is equal to the data that I'm trying to delete, then break out of the loop. That's what it says. If not, then go to the next one. So with this while loop, we're always checking one ahead before we navigate. We're checking the one in front of us before we actually navigate there. So that's that. So once we break out of the loop, that either means that we found the target or the target is not in the list. So we create a temp pointer called target, and that's equal to the next. So that's equal to the next one, the one that we checked and found. This part of the while loop will break out of the loop if we have a target. So this target would be either null or the actual target. So we do that check. If it's not null, that means we actually have a target that we want to delete. So we say the temp.next, we're saying temp.next, which is the target right now. Instead of that, change it to the targets.next. So we're changing it to targets.next. So what this is doing right here is saying the previous one is jumping over the one that's going to get deleted. So the previous one is pointing to the one after the one getting deleted. Then we delete the target, and then we make the length go down. So that's the delete item. Now, like I said, if you don't understand this, I'm going to draw it out so that if that helps. But also ask me questions, because you're not going to find this solution on the web, and there may be another solution, but it's hard to find these kind of solutions. There's really just aren't that many. You have to understand it and think of it your own. I wrote this delete myself, so other people might have other ones. I don't know, but they're hard to find. So ask me questions if you don't understand. So let's go ahead and go through this again, but I'm going to draw it out this time and start fresh. So let's go ahead, and I'll try to keep this as neat as possible. Let me just start it up. So we have start, and I'm going to say my pointer has 3 nodes, and we're deleting them. That's what I'm going to say. So we have 3 nodes. And I'm going to give the values in each one. So let's say this one has the value 5, and this one has the value 6, and this has the value 7. So 5, 6, 7. Now I'll set up the links. So the start is pointing to the first node. This is pointing to the next node. This is pointing to that node. And this node is pointing to ground. So this is our setup, and our statement is we want to delete 6. So how does this work? So I'm going to read it line by line. So the first thing that happens is start null? No, it's not. We're good to go. No type temp equals start. So temp equals start. So let's go ahead and make another temp pointer. Temp is right here, and temp equals start. So temp is now pointing there. It says if item equals start.data. Our item is 6 because we're deleting 6. So it's saying is 6 equal to 5? No, 6 is not equal to 5, so we're not deleting the first item. So we get into the else portion. Now that we're in the else, we hit a while loop, and it says while temp.next is not equal to null. So temp.next is 6. Is 6 null? No. Or is temp.next null? So is this null? No, it's not. It's pointing to 6. And while items.next, while item is not equal to temps.next.data. So while item, which is 6, is not equal, so it goes temps.next, which is this .data. So it's saying while 6 is not equal to 6. Is 6 equal to 6? Yes, it is. So at that moment, we break out of the loop. We never even enter the loop, because the while loop, it checks if item is not equal So the while loop continues while item is not equal to temp.next.data. So temp.next.data is 6 right here. So they are equal, so it breaks out of the loop. So then we have that. So we go node type target equals temp.next. So we create a new pointer called target. Target is equal to temp.next. So temp.next is 6. So target is pointing at 6 now. If target is not equal to null, then temp.next equals target.next. So that line of code is saying temps.next, which is this right here. Let me go ahead. So it goes temps.next equals targets.next. Temp.next equals target.next. So targets.next is 7. Temps.next, I'm redirecting that to 7 now. So that's where we get that loop right there. And we're passing over 6 now. Now that we have that, it says delete target. So target gets deleted. And then length minus minus. So this picture efficiently deleted target, and now 5 is pointing to 7 properly. So this is how you do it. This is the proper way. And if you check to see if it's, even if the item is not inside of this, it still works if you want to try that out. So this is what the delete function is doing. So now that we program the delete, show, get length, destructor, make empty, is full, insert, and a constructor, let's go ahead and write some code to make this work. So let's go ahead and make an unsorted type, UST insert item 5, 6, 7. Let's do UST.show first. Oops, wow. I can't believe I just did that. I forgot completely that I can't do that. Let's go ahead and run that. Now notice they're being displayed backwards because remember we add the items to the front. So 5, 6, 7. So 7 is the last one to get added, so that's getting added into the front. That's why it's saying 7, 6, 5. Let's go ahead and delete an item now. UST.DeleteItem. Let's delete 6 and then run that. As you can see, it says 7 and 5. We properly deleted it. Let's try to delete 65. That's not in the list. Will the program crash? I don't know. Let's see. Nope. Those 3 are there. We didn't delete anything because it doesn't exist. The program didn't crash. Let's try to call get length. So let's go. Actually, and let's go. So run it, the length should be 3. It is. Let's delete something before that. Let's do UST.delete 6 and then call the length. Now length is 2 proper. Let's try UST make empty, then length, and then show. So the length should be 0 in this. And nothing shown because we made it empty, which deletes everything. And I think that's it. I mean, is full, it's going to return false because it's not full. But yeah, that's everything. So that's it for this lesson. I want to keep it as short as possible. You know, it's pretty long. We did the same thing. We did the same container or collection type that we did in the last lesson, except the last lesson used an array-based implementation, whereas this used an linked list implementation. And we talked about the pros and the cons, how a linked list is better if you're going to be adding a lot of items, but it has some cons because you don't have random access, and if you want to get to a certain thing, you have to go through the entire thing, which is going to get you a big runtime of n. So if you have any questions, which I'm sure some of you guys have, because this is not the easiest topic to understand, especially that delete function. If you have any questions with that, go ahead and let me know. But yeah, for the most part, that's it on this, the basics of linked list. We will be doing more and more with linked list when we talk about stacks and queues, and then binary search trees, and so on and so on. There's a lot more, and we'll be using linked lists all the time. So try to get this, try to understand this, and then you'll be good to go. So thanks for watching, and be sure to check out the next video.